So let me have a review for the algorithm and the machine itself. I will show several examples of this plastic lesion and neoplasm, and how, especially how the dosi sees it, and what will be the imaging it produced. So this article, as you can see, was published in Journal of Biomedical Optics, and I'll jump right away to the method the machine works. So what I'm doing is actually using different kind of polarization in the light source and different kind of polarization in the camera, and produce a mathematical differences between them. So, for example, if this is the sequence of my imaging, when every picture is a different polarization and not just two, like the well-known methods today, here the main difference is that I'm using a lot of kind of polarizations and trying to extract from them the scattering light, symbolizing the areas which have high distortion and low distortion, and I'll show it in a minute. So, for example, a regular lesion can be emerged as using this algorithm, of course, can emerge as a hazy picture. When we saw that the majority of the picture, like 99.999% of the picture that wasn't dangerous, means low neoplasm, the inner part of the lesion looks like smeared or like a hazy picture. In the article itself, you can read about the algorithm, which I don't think it's the place to extend about this. It can be given and explained in video conference or WebEx. So every lesion that was scanned, of course, passed the biopsy, and we used the knowledge of the histology people and analysis the structure of the cells, of the fibrils, and the structures of the melanocyte cells. And we saw that, for example, junction nevus, there is here two examples of junction nevus, which not considered as a dangerous one. We see that the lesion here in S, it's the source, and the middle column is taken in first algorithm, and this is the second algorithm. The first row here, where you see G, it's in green light, and here it's in red light, which is more penetrable. And the inner structures looks like hazy pictures, especially the second algorithm. It does not produce strong structures in it when the lesion has a low neoplasm or dysplasm, excuse me. It's probably more correct to say dysplasm. Of course, in the stage of neoplasm, for example, I'll jump to this malignant melanome. So one can see a very prominent structures inside the lesion. Here the lesion just covers the whole field of view. But when one look with a bare eye, you won't see this kind of structures. But checking several cases, we could realize that, for example, this is also another lesion with malignant melanoma, and this is another one. You can see very decisively that the inner part is first totally different from the algorithm and the picture itself when I see it without the machine. So dosi can produce wonderful pictures to follow up a lesion. We can see it something like this. When we start to see this kind of change, this change from an innocent or hazy imaging using our algorithm can during the time start to be distorted underneath the skin and degrade to something that looks like trenches or snake-like, as I like to say. And the idea is to give or to enable the patient to follow in his own time on himself. So he will have the machine in his house or in some station or whatever. But the ability to follow yourself and see in your own eyes how the lesion starts to be distorted underneath the skin, this by itself can save life. Why? Because research shows that more than 30% of the cases, and of course people say maybe different percent, but more or less, at least what I saw, that there is some steps before the lesion become malignant melanoma or with hard neoplasm. The dysplasm before the final degradation or change in genome and producing cancer cells, the changes are very clear to be what we see here. I mean, some distortion underneath the skin. So once we enable people to follow themselves and to catch this distortion before it degrades to cancers, I think we can save life.